Before I start is who has already performed some molecular dynamic simulations? Raise your hand. Who hasn't? Okay. So I can ask you direct questions. So my first question is why we run MD. Why do we do that? There's a lot of people doing MD simulations, so why do you run MD simulations? Tell me.
Can you repeat the question, please?
Why do you run MD simulations? What's the reason for running MD simulation?
Because it simplifies the real lab work. Instead of doing hard work that you cannot actually see inside, you can run MD simulations and you can see what actually is happening.
Yes, so what is happening? That's the key part. So you see dynamics of the system in time. Of course, we do it computationally because it saves money, obviously. Otherwise, we wouldn't do it. But that's because I'm not covered in my presentation, or actually two presentations.
Tohle to strčit do USBčka. So before Petr starts, there is just 11 people who would like to go to the excursion, right? Nobody else, because you haven't signed your sheets. So for that reason, I will leave the sheets to be signed. You have to have all if you would like to go for the excursion this evening. Otherwise, only those 11 people can come. Okay. Máte daleky.
Neukazuje. Neukazuje. Ukazuje. A jenom.
That's all.
Hodím to.
Dobře.
Chceš to druhé prezentovat?
Aha.
Jsi začal?
Jo?
Ne, to nemůžeš.
Once again?
Yeah, start again. I can introduce you, right?
Okay.
So that was a fresh start, and now we can start for the recording purposes again. So the next presentation will be dealt by Petr Stadlbauer about the introduction of molecular dynamics and what to do and what not to do during setuping and simulation of molecular dynamic simulations. So, Petr, the floor is yours for the second time.
Thanks. Right, so I've already asked you why random distributions, so let's skip that. And my talk is divided in two parts. First is like basically description of the method. But since most of you are computational chemists, so it's just a brief introduction. And I expect you that either you know it already or you don't know it, but you have computational background, so it will be easy for you to follow. And the second part is what to do and what not to do when running MD simulations. I apologize, my presentation is actually divided into two separate files because of some compatibility issues between PowerPoint and LibreOffice, so Windows and Linux. So okay, so what's the logical part? Yes. Okay. So molecular dynamics is essentially based on solving these with the Newton's second law of motion. We have some whatever. I won't use it, sorry. Mass times acceleration equals minus force. It's the gradient of the potential energy. Where do we get the potential energy? From molecular mechanics. Get to that. And what we have to do, we solve these equations in time. So we get how molecules or the particles move. How a typical MD algorithm works. For the numerical integration of gradients happens actually here, but this is the most important part from the previous slide. But the rest we have to somewhere start, get the model somewhere. Then we find which atoms or particles. I'll be talking about atoms because I'm used to all atomic models, but it of course applies to coarse-grained models, so there may also be some beats. So first you find where your atom is and what its neighbors are. From there, you get the forces. That's where the molecular mechanics comes in. I'm talking about optical forces. So you get like bonding interactions, electrostatics. Then you solve the equations. Usually we perform some pressure and temperature control because we want to run the simulations at defined conditions. And then we move forward in time. If necessary, we calculate some quantities like the pressure or some energies. And then our question is whether we have reached the final or our desired number of time steps. If not, the whole process repeats. If yes, the simulation ends there. In the cycle, many times. Okay, so what is molecular mechanics? We describe molecules by standard score, speeds and strain model. That's how we usually do it. The advantage is that this simplified approach allows us to describe, for example, millions of particles in one system, which would be impossible to do in quantum mechanics. And of course, you can apply various level of approximation. This is from the least approximated to most approximated. So polarizable atom models, non-polarizable united atom models, or some even more coarse-grained models. So here's an example. This is an atomic model. Here, every atom has its own particle. United atoms, no hydrogen, obviously. You have some coarse-grained models. So this model, you can see the level of description. It's of course then courses, so you have to bear in mind that by this model you cannot study conventional hydrogen bonds. So, but can describe like a cell, whole cell, for example. Okay, so when talking about particle, some properties. So one of the properties is charge. Usually we have a charge fixed in the center of the particle. It's a point charge. It's an artificial quantity, Oh, sorry. It should be here. Usually it's from electrostatic potential calculation, so from QM. Okay. Then it is mass and shape. Mass, when it's carbon, its relative mass is 12. When it's oxygen, its relative mass is 16. And shape and size, when we have atoms, there usually are isotropic, it's spherical symmetry. It's common to say that they are spheres, but they are not spheres. They have spherical symmetry, but it doesn't mean that they are spheres. It's not like a hard ball. They have infinite spread, or a certain locus field. Propane models may have some more specific particles like cones. Okay, how we describe interaction with these particles? Our potential energy, and now we have non-bonding terms and bonding terms. So as I already drawn here, so the bonding terms are typically modeled as particles on a string. So we have torque constant, which is like the string is tough, and measure the particle where the particles are away from their equilibrium position, and this gives us the energy of the system. So the bond is typically described for angles the same, but the spring is between kind of angles between three atoms. For torsions, we have this Fourier series by which we can describe any shape of the torsion profile that we want. You can add up multiple sine and cosine functions to give you anything you want. And then here are those non-bonding pairs. This usually for electrostatics. We did by the Coulomb law. Simple. And this is called the Lagrange potential. Describes what van der Waals interactions. It's also called 12-6 or 6-12 potential. You can see some two parameters, sigma and epsilon, where the optimal distance between atoms is and how energetic it is. So this is a typical this set is one thing that we call force field, number force field. Typical classical force fields are usually of this form. They may contain some additional terms for hydrogen bonds, but it's like, for example, amplification. There could be a term for polarization, where the atom, when the charge is fixed in the center of the particle, but it can be moving around. Sometimes this expression for this expression, here are equivalent expressions. So, for example, in the force field, the parameter set in amber, you can find these terms A and B. So it's the same, but it's a different algebraic expression. So where to obtain parameters? First and foremost, we should look at experimental data. From crystallography and rotational vibration spectroscopy, you can obtain the equilibrium distances, the force constants. From QM calculations, we usually obtain the torsional parameters and charges. You can apply machine learning. This is a general term. You can apply machine learning, but here I mean we can, for example, learn the charges. If we know the charges from some set of molecules, we can learn charges, and instead of running QM calculation to obtain a set of charges for our desired ligand, we can like this machine learning. The key when obtaining these parameters that appear in these equations is that there is a limited transferability. When you obtain parameters for, I don't know, small organic molecules, you cannot apply them to some inorganic molecules, obviously. So always bear in mind that the set of parameters, which is also called the force field, so we have a force field, a set of equations, and force field, a set of parameters. But the force field is trained on something and should be used only for that. So if my system, if my force field was trained on proteins or nucleic acids, I use it for proteins or for nucleic acids. I should use it for description of some small ligands. Okay. Once I have my system, I need to somehow put it into an environment. So I should solidate it, unless I want to run it in vacuum, of course. So you have like implicit and explicit solidation, microsolidation, hybrid. So implicit solidation is basically.
Hola, vale.
Okay, whatever. And we have a I think that's correct. To mute myself is probably not the best idea. And these implicit solvents are, for example, Spossel, Boltzmann, and generalized Born models. If you don't know these, I intentionally use these abbreviations here so that you know that these two are implicit solvents. We have explicit solvents. Explicit solvent is simply that the molecules are physically present around your molecule of interest. Here are some models, take XP, SPC, OPC, for example. There's many more. Of course, these models differ by their mathematical expression. They work, these models differ by their shape, extra points, by their capture or something, and I'll show you later that more particles doesn't mean better performation. We have our system solvated, not in implicit solvent. With implicit solvents, we go to forever. But when we have explicit solvent, we typically use the boundary conditions. Boundary conditions are necessary for treating of conventional electrostatics. And of course, we want boundary conditions so that our system won't evaporate. Because when we have, there will be nothing, water or whatever would like evaporate, and then our molecule would again be in vacuum. The boundary could be hard. It means when particle reaches it, it bounces off and returns. Or it can be periodic. It means when we go from this particle, for example, goes from here, it appears on the other side. Then we have something called the integration time step. So how much should we move forward in time when doing the numerical integration of those equations of motion? So this step shouldn't be too long, it shouldn't be too short. So what's the optimal value? It depends. It should always depend on the fastest motion in your system, which is typically the vibration of the CH bond. And the vibration period is about 10 frames per second. So it's when nothing else is applied. Safe choice is 1/10 of this value, which is 1/10 per second. Then there are some algorithms, like shades and lakes, which allow you to decrease this value to 2 femtoseconds. Typically, it's this way, and they basically station the vibration. They don't allow the hydrogen to move that much around this heavy atom. And it's applied to like anything that is bonded to, or to all hydrogen that are bonded to some heavy atoms. While at normal temperature, of course, when you increase temperature, the vibrations get faster and faster. So when you run simulations at 400 Kelvin or 300 Kelvin, then you should be careful with 2 femtoseconds, even with like shading, stuff like that. There is something called hydrogen mass repartitioning, which redistributes the mass between hydrogen and the heavy atom, and redistribute the mass. The vibration gets slower, so you can increase your time step to 4 femtoseconds. Again, it's not like one size. You cannot apply it always. For example, when you have ligands running into a deep channel, it's typically when you should know hydrogen mass repartitioning. If I'm correct, you shouldn't use it with membranes. But I'm not running membranes, so I've learned as well. We have virtual interaction sites that allow us to increase the time with fine femtoseconds. So why the step should be too short is obvious. When the step is too short, then I have to run many cycles to get some reasonable time. But why not too long? It's because suppose I have particles here, and there is force acting on them this way. So when the time step is too long, the algorithm would tell me, okay, so after a certain amount of time, given the acceleration and velocities, they're in a position like this. Now they are very close. So at this point, there's a strong repulsion, so the forces are like this. So after the same time step, now the particles are here. When the particles are away, the spring is pain very much, so there's even bigger force when you put it back. So eventually your system would explode. It may in the simulations, of course it crashes, but before it crashes, you would see like some crazy prolongation in the system. Okay, so the oscillation, we want the system to be electron neutral. Otherwise, for example, the particle methods for the calculation of electron wouldn't work. But then also, we want to add ions to mimic the environment. Like, for example, 150 millimole KCl inside cells. we want to apply temperature and pressure control, typically 300 Kelvin or more or less like that, and pressure of 1 atmosphere for the thermostats and barostats. I'll get to them later. So this is the classical MD simulations. This is a deliberately put here paper from 2010, so we are 15 years later. So we have moved from here, like the length available MD simulations to here. Not sure if it's much, but there's some progress. The main limitation of plain MD simulations is that they can hardly overcome some free energy barriers that are high enough. So for that, there are some enhanced sampling methods. Just to let you know, who doesn't know. So these methods aim to overcome these barriers. So we have some umbrella sampling based methods, where you apply additional artificial potential to keep the molecules out of their energetic minima, bring somewhere else. Probably the most used method now is based on umbrella sampling, is metadynamics. There's currently this on-the-fly probability enhanced sampling, uses kind of similar, it's conceptually different approach. It's also like where we modify this potential to obtain the desired probabilities. It's kind of like metadynamics, but not exactly. What's important here that we have something called the collective variable C, and we bias the potential along this collective variable. So we have enhanced sampling. Just this collective variable could be, for example, distance between two atoms. So this enhanced sampling happens only along this collective variable, not to anything that is orthogonal to that. By orthogonal, I don't mean like geometrically, but in terms of the potential. Other set of methods, based on parallel tempering or replica exchange, where we have like multiple replicas running in parallel. This is from the colors are counterintuitive, sorry. This is from the coldest to the hottest, and you run them at some time intervals. You swap them based on some based on some statistical criteria, whatever. That's not important here. So what is important here is that at higher temperatures, you get higher probability of overcoming some barriers. And at lower temperatures, you have your desired probability. And the molecules can move up and down, and eventually your probability distribution of states, your reference temperature, which is the coldest one, or the one that is in the body, be your true converse probability. These methods, they work fine on small systems, but when your system gets bigger, it's basically impossible to take convergence, unfortunately. So that is probably okay. So the force field for small molecules, there are some net force field, general under force field.
Yes.
Seven choices that I like kind of recommend. For biomolecules, we have this 21 for DNA, maybe now it's 24 or 4, but this was used really for RNA. It's complicated. For proteins, usually two force fields. This one is better for some disordered proteins. This one is better for globular proteins. And this is here just so that I don't annoy people. And Martin is a typical coarse grain force field. It's used with membranes. And programs very usually around production and like large scale industries, so blue math is used for those enhanced sampling with metadynamics. Okay, now we have a few minutes to go through the do's and don'ts. Okay, so this is more practical. So these are most important rules. Always read the manual. It sounds silly, but always do it. Always visualize your input structure. Examples, why not? Always visualize the output trajectory. Some people don't, I don't know why. And always think about the results critically. It's an approximation, so think about it critically. So, for example, in this figure is from this paper, but it was maybe 20 years ago. Some guys published this novel structure of RNA. Of course, it was the first artifact, but it was published as a novel structure of RNA. They failed this step. So, once the first use was corrected, this structure never appeared again. Okay, when you have an input structure, always validate chiral centers. It applies for ligands, it applies for biomolecules as well. Always inspect predictive structure, even if AlphaFold says it's confident that it's right. I have encountered many AlphaFold models when it showed the blue high probability, but the structure is wrong. So always do that and think about whether the structure makes sense. For example, there could be close contacts, means overlapping atoms, intersecting chains, some nonsensic hydrogen bonding and stuff like that. So this is why visualization matters. So this is RNA, and you can, for example, see, okay, this is the first image that shows up, and you want to download it and run enzymes, and that's okay, this is nice. Oh, and this is like nice. You can see it's slit. It's not like two separate, because this strand is bound to this strand. But when you actually do the step that I recommend you, inspect the structure, you see that it's like that. It's not like that, because this is biological assembly 1, then there's biological assembly 2, and there is asymmetric units. And what is shown here is not what the actual structure that you download looks like. So this is it. That's why you should always not rely on this picture. Always inspect it. When you have proteins, always run specialized the checks for the protonation states of histidines. Because you can see the proton. There is hydrogen, hydrogen on this side, hydrogen on this side. It depends on the partners in the protein where the hydrogen bond should be. Why these two amino acids should be inspected? It's because when it comes from X-ray, they don't see hydrogens. So what they see is carbon, and something is here and something is here. And then they don't know whether it's this amide group and this is oxygen or whether it's swapped. So it's guessed based on the environment. So always check it. You yourself and buy the software. Solvent, but there's a lot, it's not just some stuff around. Unless you know what you are doing, avoid implicit solvent in the age of GPUs. Just don't use it unless you really know why you want to use it. But still, here's an example, explicit solvents. So these are models here. And what you can see is that this is RMSD, I mean, basically how the molecule deviates from some reference state. So you can see the red curve. The molecule is unstable. This is protein RNA complex. Then we have OPC. This is also somewhat unstable, and it's totally unstable. And these are like 4-point models, which are supposed to be better than the 3-point models. And when we have these two 3-point models, you can see that the molecule is quite stable. So when you run simulations of whatever, proteins, nucleic acids, membranes, really go into the literature and find what is the best, find some benchmark studies and find what is the best parameter set. Do not always follow the manual in this, especially if the manual is old, because it may be obsolete already. But for example, the best, so far best RNA force field is at this point like 12 years old already. Nothing better is clear. Ions. Make sure that the ion parameters that you use are compatible with the water model. And always visualize them in your simulation. Do not strip them away. When you strip water, never strip the ions, because you might miss artifacts like that. This shouldn't happen, crystallization, but if you load wrong parameters, this can happen. So I've seen it many times. It's also good for checking your binding sites, because there could be binding sites not only where you expect it, but also somewhere else. Try to avoid possible multivalent ions. It's because they're high charge and they basically act like a glue or something. Magnesium, and you have something negative, it sticks to it, and it's a problem. The treatment is that we can artificially reduce the charge of these. It applies not only to cations, even this could be like charged amino acids. We can scale these charges down, like avoid these excessive sticking. But the drawback is that this is structure specific. So it applies some certain conformation, but if your conformation changes and you have still have scaled charges, now it might behave in the wrong way. So careful with that. And the typical problem is when we have like multiple binding sites close together. There's usually an excessive repulsion of the like charges of plus next to another plus. They don't like it much. Okay, so this movie doesn't work, obviously. But for what I want to show you, instead of calculating density map of ions, you can just load the trajectory and visualize every step or every other step and see the position of ions, and then you can visualize. This can help you visualize whether there is higher density ions. So it's not like the proper calculation of some densities on the grid, but it helps you visualize where the ions are. For thermostat, avoid direct cell scheme. Thermostat, it's complicated. There's some like Monte Carlo bars that should be used for periodic battery groups, but should be used for membranes. So please follow some guidelines that are in the literature. Regarding analysis, always inspect the trajectory. I often review papers from some countries, and the whole analysis is just we ran these simulations, and here are RMSD plots, and that's it. Like, okay, so what's going on in the trajectory? So always inspecting, because not only it helps the reader to understand much better what's going on in terms of plane graph, but it may help you find if there's some weird shapes, artificial of course. There could be improper imaging when there are conditions. In some part of the molecule will move from one side and appear on the other side. We would see it in the trajectory. Improper imaging, that means we return it back to the center so that it doesn't like move away and disappear and appear on the other side. So it's just a continuous movement. Of course, if you run some analysis with improper imaging, you could get some nonsensical results. Like for example, distance between atoms may suddenly measure distance between atoms in your protein. Your protein goes here. Suddenly this atom is here in this periodic image and the distance is measured as this. So that's why you should utilize trajectory. And again, even now, check hierarchy, because it may change especially during setup, means when you start at the beginning of your simulation, when you heat it up, there is low but still possibility. I've encountered it several times that there could be some strain in your molecule that can swap the chirality, and then you're basically you can run the simulation again. Unfortunately, but always do it. So RMSD. It's probably the most overused metric in the papers. So what can we see here? How to interpret it? And some students tell me, what does this mean? Like for example, this screen curve, I took it from the internet. Yes.
That there is a bit of conformational change
Yes.
from the time, so t, and the structure that you are analyzing. For example, in the first one, there is a change from time like 1.
Yeah, fine. There's a conformational change. It doesn't mean the molecule is unstable. That's what I often encounter. It could be unstable, but it's not necessarily unstable. So this is a conformational change. And then when we have higher RMSD, the conformational change, there could be some conformational changes even here. But since we are farther away from zero, then this metric becomes less sensitive. I also encounter graphs that look like this. You know what this means? This is RMSD curve. If it goes like this, this is RMSD and this is time. What does this mean? It means that this molecule is before RMSD was not fitted. Yeah, when you run before running RMSD to make sense, unless you want to analyze some diffusion, you should always the algorithm typically do it. You should fit the molecule on the best fit of the molecule to your reference conformation. Okay, another overused analysis is this principal component analysis, PCA. I often see graphs like this, and that's it. What can you understand from this? So yes, there is some, but what's its meaning? We should always accompany these figures, which show what the correlation is. And there are some more tricky stuff. Do not trust this software foolishly. So, for example, Amber software is managed to route incorrectly. It measures sugars incorrectly. If I'm right, GrowMax doesn't calculate this lateral diffusion correctly as well. But there are specialized tools for that. So not always, when running these kind of more specialized calculations, try to look for specialized software for that. And then PBSA is also a method that is very overused, and it's not that good as it seems even if you're, and especially when your molecules are bigger, because this method is very sensitive to noise, small population changes. So if you want to use it, please use it only for small ligands. And if there are structural ions in the structure in your molecule of interest, let them be there. Do not strip them away as possible. Let them be there. And when evaluating these free energies, treat them as some relative measure, not as some absolute delta G's. Sometimes see, okay, this delta G is some crazy numbers, like, okay, this delta G is 200 kcal per month. What? This is a nonsense. Okay, so to conclude, always check your structure, look for the best parameters for your problem, and evaluate the results with a grain of salt. That's it, and thank you for your attention. If there is a lecture after here, yes. I think you can, or if there are questions, just ask, or you may ask me later. We can discuss. I think we should probably move on.